Chapter 1 continues with a review of design data, and in this section of the lecture we're going to focus on anthropometry in particular. There have been a large number of studies that have collected anthropometric or body size data on people, and so our goal is we have these studies, we have these measurements, we don't need to retake them ourselves. We know what people measure, we know their sizes, and so let's apply this information, the data that's already available to us, so that we can ensure that we accommodate a large majority of the potential workforce. That statement brings up a couple questions. Why are we talking about a potential rather than who we currently have? And one reason for that is, let's say that somebody that you employ that you fit exactly retires, you hire somebody new, and you really hadn't made sure that your equipment would accommodate a large majority, and so they don't fit. You have to go out and retrofit or buy something new. It gets to be more expensive, and so if we could fit the potential workforce, then anybody you brought in would be more than likely to be accommodated already. By fitting a large majority of the potential workforce, you're also reducing fatigue or exertion levels because you're designing for the majority. Since you're designing for the majority, meaning some of the weaker, some of the people that would fatigue more quickly, they can stay on the job longer as they are aging. And then if you do have that turnover, you'll be sure that people would be accommodated. Okay, so that's why we fit the potential workforce. But if we take a look at large majority, what do we mean by that? And so if I were to ask you what percent is a large majority of the workforce, meaning what percent do we want to accommodate, your choices run 1 at 51% down through 7 at 99.5%. Answer to that is pretty much it could be any of those. As we're trying to make use of some of this data that's been collected following design guidelines, it's more of an art than a science. Some of these things are open to interpretation. Some you'll have to apply reasonable guidelines for reasonable use, and so your goal could be any of these. So looking at anthropometry, the study of human body size dimensions, I want to do a review. You've probably studied this before, and so if you turn to page 52 in your book, page 52, we're looking at if we were, for example, to design the height of doorways. Which dimension, and so these dimensions will be numbered, which dimension would you want to use to design the height of a doorway? And so you start looking at what is the critical task. The critical task is you have to walk through the doorway, you have to pass through. People pass through standing upright, and so you have to fit the largest dimension as they're standing upright. And so at a minimum, you're wanting to fit, the answer for this is number 9. They have to be walked through so that the top of their head gets through the doorway. So we probably everyday life, layman's terminology, we call this standing height, just the distance from the bottom of our feet to the top of our head. You see on our table, quick refresher, we refer to that as being stature. So number 9 is stature. Next question is, which anthropometric dimension is used to specify the highest vertical placement of a control? And so you can see the woman in our workplace reaching for this control. What's the highest vertical placement of control if we're using it only infrequently? And so again, you go back, quick refresher, which dimension do you think you want to pick? If it's only used infrequently, she can reach over her head, and so you're looking for an overhead type of thing. She's reaching with an arm, so it's going to be an overhead reach. And then the last thing is we try to make it functional meaning a closed fist, so that an operator can use the control. And so the answer to this is number 10, a functional overhead reach. So number 10, functional overhead reach. Looking at a very similar problem, the anthropometric dimension used to specify the highest vertical placement of a frequently used control. And so the only thing to change on this question is now instead of infrequent use, now it's frequently used. And you know that if you start raising your hand above this full functional overhead reach, you raise your hand above your head a lot, do any sort of operation, your shoulder is going to wear out. And so you don't want that to happen if you're using it frequently. And so we bring things closer to our body, closer to our trunk and torso when we use things frequently. And so in that case, the highest you want to go, this is kind of one of those rules of thumb that you apply, the highest you want to go is your shoulder height. And so looking at our numbers, that is number 7 is shoulder height. Okay, so that's a quick review. I'd urge you to take a look at the other dimensions. Look at the figures and then the table so you can match up names and locations of these. Next question, on whom will you base your design if your goal is to accommodate the largest percentage possible? In the undergraduate class, we often talked about we're trying to fit or trying to accommodate 95% of our users. So 95% is often our target goal, sometimes 90%, but typically 90 to 95%. Knowing that we want to fit or accommodate 95%, we still have to go back and select that percentile to fit 95%. And this percentile that we select will depend on the type of dimension we have. And so it does differ. The percentile we select, whether it's a 5th percentile, a 50th percentile, a 95th percentile, which one we pick is going to differ depending on the type of dimension we have. This doorway example that we did, the doorway in which we're trying to fit somebody through a hole, they're trying to fit into something, that's known as a clearance dimension. So I'm going to go ahead and just mark that doorway fit. So clearance, we have to fit people through, we have to clear them through. Okay. So that was the first one, and so that was by our stature. The top of our head has to fit through the doorway. The next two examples where the woman was reaching for a control, either reaching overhead or reaching to shoulder height, those are known as reach dimensions, and we typically reach with our hands and arms, or with our legs and feet, or we could reach with our eyes. Okay, so those are reaches, and in that case we would be accommodating a different percentile person, figuring that if a small person can reach it, then everybody with longer arms can. And so a reach is a to get to. Average will come back. Average will just be the typical user, the middle user, the 50th percentile user. And then lastly, adjustable. Anytime we have adjustable, we try to fit it so that the small person and the large person can use it. Okay. I've been talking percentiles, and so I just want a quick refresher. Percentile is the percent of the people smaller or equal to that measurement. So the percent of people smaller or equal to that measurement. And so if we're looking at who do we base our design on, if we try to meet that rule of accommodating 95% of users, if we're trying to do that, we need to choose the percentile, for example, for a door height. And so if we're fitting percentiles down on this bottom percentiles, if we fit the first percentile, then that means anybody shorter or equal to that first percentile can fit through the doorway. And so that would only be 1% of our population can fit. So 1%. That's not enough users, that's hardly anybody, and so if we moved it up and based it on a 5th percentile, so that 5% of those smaller can fit through, we would only have a total of 5% fitting. And again, not very good. And so if we move it up to 50th, the middle of our population, assuming I could draw a straight line, you would fit the people that are the 50th percentile and shorter. In that case, you'd fit 50%, so you'd fit half of people, and you'd find that Anybody taller than the average would bump their head. So again, not good. And so if we want to fit 95%, we would fit the 95th percentile. 95th percentile. Okay, if we fit the 95th percentile, that means the people that are in the 95th percentile and shorter would fit through the doorway, and so that's a total of 95% accommodated. And so for clearance dimensions, we typically base on a large percentile, 95th percentile, that will accommodate that same percentage. The second one, the highest placement of control, we identified that as being a reach dimension. And in that case, if we base it on a first percentile, the first percentile arm length, that means that these people can reach it, these people with longer arms can reach it, and only the people with shorter arms cannot. And so first, if we're trying to fit 95%, first percentile is really too much, is really accommodating too much of the population. If that dimension has an expense associated with it, it might be too costly. And so if we're trying to fit 95%, we can instead move to the opposite, not the opposite, but move up, that if we set it for a 5th percentile arm length, then anybody with longer arms on this side can reach it, so 95% can reach it, and 5% now cannot. 5% cannot. Okay. If we had based it on a 95th percentile, just like we did with the clearance, then that would mean only the 95th percentile and larger could reach, and that would only be 5% total, and so the 95th percentile is not a good answer. Instead, we want to base it on the 5th percentile. Last one, the example is width of an airplane seat pan, and the seat pan is what is the part of a chair that you actually sit on, that you put your buttocks on. Okay, and so you want to know how wide is an airplane seat, and so that becomes, out of our examples, is that a reach or is that a clearance? Do you want your thigh to thigh, so the width of your buttocks, your buttock breadth? You go to your table, you can see that's dimension number 25 is hip breadth. Would you want to base this dimension that is not adjustable? Would you want it to base it on slim hips? So still going for that 95, would you want to base it on slim hips, or would you want to base it on wide hips? The airplane manufacturer probably would save building costs, they would save the expense of the seats, they would save money if they actually built it on slim hips. There would be less product cost. However, their customers wouldn't be able to fit their buttocks into it, and so they wouldn't be able to sell as many seats. And so in this case you'd want to fit for the wider hips, so that it will accommodate more customers. More customers will buy tickets, they'll fit into the seats, and so in that case you would base this on a 95th percentile hip breadth. You'll be sure to accommodate the wide hips, but also the thinner hips. Okay, so that's the basic concept. Now if we move into looking at how the table is set up, and this is on page 50, 51, 52, the table is set up to give you these dimensions. So they've listed dimensions 1 through 25 on one page and continues on the next page. And then across the top, the headers across the top, they're going to start by giving you 2 male columns, 2 female columns, and 3 50-50 male-female mixed columns. Okay, so 2 male, 2 female, and then combination of 50-50 male-female. Page 50, you have your information in inches. Okay, so page 50 is in inches. There's a table that gives you metric. There's a table that gives you the inches and pounds, and so I'm referring right now to the inches and pounds. The two male columns, they give you a mean, average, 50th percentile, so those are all synonymous, a mean, average, and 50th percentile, and then they'll give you a standard deviation column. And so this first column tells you that the average male height is 68.7 inches. The standard deviation of this height is 2.6. The next two columns are females, and so the average female height is 63.8 inches, and her standard deviation. Okay, and so working with those male-female dimensions first. Considering the average height for only your sex, if you're male, look at the male data. If you're female, look at the female data only. Are you taller, shorter, or right at average? Okay, so if you're males, you're looking at this. Females looking at this. Okay, so I'm 5'6", which is 66 inches. I'm female, and so I would do this comparison, and so my answer would be I'm at 66 inches is taller than 63.8 inches. So I'm taller than average for my sex. Okay, so we have male information, we have female information. Well, in your workplaces you have both males and females. And so they will give you a set of data that is a mixture of males and females, and in this they've just broken it down to be 50% of the group was males, 50% of the group was females. Okay, and so next question, if we were to compare you to this set of data, the 50-50 mix, are you now, we have a new average since we have half males, half females. You can see the average is shorter than the male average, but it's taller than the female average. Okay, because you have a 50-50 mix. And so now are you taller, shorter, or almost exactly average for this 50-50 mix? And going back to my information, I told you I was 5'6", I'm 66, and so I'm almost exactly average. And so typically, as I come into contact with equipment, with tables, with desks, with chairs, with equipment that is based on a height dimension, usually it fits me pretty well. I don't, my legs aren't typically dangling, my head isn't getting bumped, I'm almost exactly average, and so a lot of the stuff out there has been designed based right on where I'm sitting. Okay, now moving on to do that door clearance, reach, control height, seat pan width. Looking back at that, now that we've identified where on the normal curve that you would fit, we want to go back and start looking at, okay, how would we use this information? And so if we go back and look at door height, we want people to be able to walk through the door without hitting their head. If we were basing this on a 50-50 mix, you want to design so it accommodates 95%. Would you select a measurement of 60.8 inches? You would say obviously no, because the 66-inch tall, the 72-inch tall people would bump their heads, so that's not good. If you think you want to base a design on average, you can see that, well, still we're going to have a large proportion of 50% people, though they will bump their heads, so we don't want to do average, so that's not good. And so on a door height, you would go for the larger, so 95th percentile. The next question, though, is this good enough for 50-50 mix, Or do we want to make sure that 95% of males are accommodated using these two bits of information? And so we definitely don't want people bumping their head. We don't want them to have to think about it. We can cut the hole bigger. And so you'd probably want to go with a male's larger than female, so with a male 95th percentile. And so we'll have to find out, how do we find that information? Second question, the maximum control height. Maximum control height, again, we can look at we have mixed males and females in our workplace, and so if we use this mixture data that we've have, you want to set it so everybody can reach, and so everybody can reach, we would want to go on the functional overhead reach of our smaller person. If that person can reach it, the other people can too. And then similarly, same concepts applied, seat pan width. We can see that if we fit wider, bigger, then smaller will be accommodated. Okay, so those are concepts using the table. And so now let's start applying this and start looking at some of the stepping through and looking at some of the data. If we take airplane seating, we know how uncomfortable airplane seating is, and so let's do it better. Let's do it how it should be designed. We'll be looking at the height of the seat pan. And again, the seat pan is the part you sit on, so the height of a seat pan is from the floor to the top of the seat pan. We're going to be looking at the depth of the seat pan is the front to back, so depths are front to back. And then we're going to be looking at the space between the rows. The space between the rows from the seat back, the front of the seat back, to the back of the seat back and the row ahead of them. So those are the three dimensions that we're going to apply this to. We're going to be looking at, if we were designing the height of a seat pan, the dimension, you know that you need to find a leg dimension that matched that. You know that the underside of your knee touches the seat. The bottom of your foot should be touching the floor, and so that height, the seat pan height, needs to match bottom of foot to underside of your leg. That is known as your popliteal height. Okay, so the backside of your knee is your popliteal area. So popliteal height will be the height of the seat pan. Okay, so stepping through, anthropometric dimension name for the height of a seat pan will be popliteal height. The percentile you want to base it on. Do you want to base it on short 5th percentile legs, average 50th percentile legs, or tall 95th percentile legs? You're going to find that, well, whenever you're flying, we're concerned about deep vein thrombosis. We don't want to pinch the blood flow, stop the blood flow, affect the blood flow in your legs. Otherwise, people can develop this deep vein thrombosis. And so we don't want their legs to be dangling in space. We want them to be able to rest on the floor comfortably. And so on a seat pan height, we will be basing it on a smaller dimension, a 5th percentile. So 5th percentile popliteal height. Our next consideration is, do we want to use a male, female, or a mixed male-female? And if we're fitting a 5th percentile, we usually want to go with the smallest, and so smallest male or female, that obviously would be female. And so our considerations are small female or small 50-50 mix. So small female or small 50-50 mix. And you have to consider, well, what if you base it on? If it's easiest to go, it's already calculated for you, and so it's easiest to go with a 50-50 mix. You can identify the 50-50 mix, small 5th percentile, popliteal height is 15.1 inches. And so like, is that good enough? What happens? Your 5th percentile female will have shorter legs, and so you look at, if you don't design for her exactly, can she be accommodated in any way? If a small female gets onto a plane, her legs are dangling, can we accommodate her in any way if our seat doesn't automatically accommodate her? And you're going to find that yes, she can put her foot on her bag. There are little stools that she can put it on. Some of the seats have fold down footrests, and she can bring, as I said, a bag to put it on. So yeah, she could be accommodated in a pinch. So it's not absolutely critical we match her. And so this 15.1 is good enough. So our value is 15.1 inches. The next thing you need to consider is, do we need to add any corrections or allowances? And for this one, you could add clothing allowances, you could add shoe allowances. I think we're limited to those. And so for this class, I want you, where they're wearing shoes, I want you to add in 1-inch heels onto the shoes. And so she's wearing shoes on her feet, which will raise the popliteal height by 1 inch. And so our final value is 15.1 inches plus 1 inch. Our final value, our seat pan, should be 16.1 inches high. Okay. This relies on you remembering from undergrad class that the anthropometric data in the tables are essentially without shoes, with bare minimum clothing, often just lycra, spandex, or cotton cloths, paper cloths, even paper robes. And so anything that you're wearing in a workplace that makes you bigger or changes your body size, you'll need to adjust for that. Okay, so we've got the first dimension, the height of the seat pan. Second dimension is the depth of a seat pan. How deep do you want it to be? Again, we go through the anthropometric dimension name. Looking at your table, you know that from the back of the seat, your buttocks are there. The front of the seat, you've got your popliteal area again. And so back to front will be your buttock popliteal length. So buttock popliteal length. Buttock popliteal length. Percentile, again, we're going to go through the same. We're going to base this on short legs, average legs, or long legs. And so it gets to be, if this dimension is too short, what's the effect? It's like nothing. Your legs can and should extend beyond this. So your legs should, so too short is okay. What about the opposite, too long? What if this is too long for your legs? Then you'll probably find that people will need to slouch in order to rest their feet on the floor. Slouching is bad for your back, and so that's a problem. And so we actually want to make this on the too short end, so on the small end. The small end, again, the percentile is 5th percentile for reaches. Their legs have to reach over it, so the 5th percentile. Sex, should we design it on, again, going small, automatically notes that we want to go towards the female, so we want to base it on a female 5th percentile, or a 50-50 mix 5th percentile. And again, you look at the 5th percentile female is going to be smaller, and so can she accommodate herself in any way if we don't design exactly for her? You're going to find that we could put a pillow behind her, we could roll a blanket, put it behind her, she could bring a bag, a coat, or something to put behind her. And so yeah, if we don't accommodate her exactly, she can do this little bit of adjustment necessary. And so we're going to use the 50-50 mix for that. And so our value is 17. We go to the table, pick off the 5th percentile 50-50 mix for buttock popliteal length. That'll be 72 inches. And so the next is, do we need to consider what we're going to use the heels on shoes? And you're going to say she doesn't wear shoes on her butt, she doesn't wear shoes on the back of her knee, and so no, we do not need any shoe allowances for this. And so your final answer will be that value of 17.2 inches. And then lastly, our third dimension, and you're going to find when you get onto planes, some of you barely have enough room for your knees. They're knocking the back of the seat. It's very uncomfortable. Airlines are reducing and reducing and reducing this dimension, and so we're looking at what should it be. And so the space between rows of seats, again, from the front of this seat back to the back of the row ahead of you, how big should that be? And you're going to find that people need to fit their legs there, They're going from their butt to the front of their knee, butt to the front of the knee, looking at the pictures, matching it to the number. You're going to find that that dimension should be upper leg length. Percentile. This is fitting big legs in, so your 5th percentile is a 95th percentile. And again, this is a clearance dimension, so 95th percentile. 95th, fitting large almost automatically. All the large dimensions should either be based on male or 50-50 mix. And so we get into the, if we design it based on the 50-50 mix, is that good enough? The 50-50, the 95th percentile for a 50-50 mix is going to be shorter than the 95th percentile male. If that space is too small, can somebody not accommodate themselves? Is there any way they can fix that? They can't. And that is essentially no. They can't chop off the front of their knee. They can't reduce their buttock size. And so no. So the 50-50 mix isn't great, and it's not a great selection in that case. And so we want to do a male, designed for the male. And so we're looking for a 95th percentile male. We don't have that on our table. So we're going to have to figure out a way to do that. Okay. To find that out, we're going to have to use the male mean, and then do something with our standard deviations that we have in the table. And so you're going to remember from one of your statistics classes that you looked at this normal curve, this bell curve. The mean 50th percentile is the center. You know if you go out one standard deviation, you're accommodating 34%. And so now you're at 50 plus 34 is 84% if you go out one standard deviation. If you go out two standard deviations, you get 50 plus 47.5, and so that's 97.5% is this one. And then if you go out three standard deviations, it's 50 plus 49.9 is 59.9, so 59.9% accommodated. Okay. Similarly, on the smaller side, you can subtract off one standard deviation and get down to the 16th percentile. Subtract off 2, you get down to 2.5 percentile. Subtract off 3 standard deviations, you get down to the 0.1 percentile. Okay. Those percentiles are close, but they're not exactly what we're looking for. And so going out by a full whole number will get you close, but not exactly. And so instead, the first page of your homework assignment, I gave you a set of formulas that basically let you calculate a larger number of percentiles. And so if we were trying to fit that 95th percentile male, we would use the equation mean, which we have in our table, plus 1.65, so that's a constant that varies by the percentile. So 1.65 times the standard deviation. Your table has standard deviation, your table has mean, and so we could plug those two in and calculate. If we wanted a third percentile, we would use this formula. If we want a 99.5 percentile, we would use this formula. Okay, so it's the same mean plus or minus some number that you would need a table for times your standard deviation. Okay, so the concept is very similar. Okay, so getting back to our problem to finally answer it, where our anthropometric dimension was upper leg length, our percentile was 95th. We decided to do a male 95th percentile, and so our value is mean plus some number times our standard deviation. In this case, I'm going to go ahead and say, well, 95th percentile maybe is not sufficient. Maybe this is one of those judgment calls. Maybe I want it a little bit larger because, well, if I make it too small, I'll lose customers. They won't be accommodated. I'll have to turn them away. I'll lose money for the airlines. And so let's say instead of 95th, I wanted to accommodate, I asked for a 99th percentile so that almost everybody's accommodated. Everybody can fit in my airline seats. In that case, my mean my mean would be 23.4, so 23.4 inches, plus for my 99th, using that table that I've showed you previously, would be 2.32. So this is 99th percentile, 2.32, times my standard deviation. The standard deviation is in my anthropometric table. My standard deviation is 1.1. And so plugging this into my calculator, I would get 25.95. Would I need to add in shoes? No, again, I don't wear shoes on my buttocks. I don't wear shoes on my knees, and so I don't need to add that. I could, if I wanted to, say that people, their clothing thickness. So they've got a thick coat on, they've got jeans on that add a little much, and so I could adjust this by an inch and say 26.95 would accommodate everybody. Okay, so that could be my final answer there. Just did want to point out, in case I lost you on the 23.4 and the 1.1, that came from, I'm going to flip back a few slides, so bear with me. That came from this table. So this table, which is page 50 in your book, the upper leg length is 23.4, was the male mean. The male standard deviation was 1.1, and so I had mean plus 2.32, the statistical referring to 99th percent, times my standard deviation of 1.1. Okay, so that was my final answer there. Okay, similar problem. How much weight should an office chair or a ladder support? So if we look at ladders, how much weight should a ladder support? You go to buy a ladder at Lowe's or at your Home Depot. What's it rated for? How much weight can a person weigh? If we go with our standard, we have to accommodate what body dimension. In that case, it'll be a body weight. So it'll be a body weight if we do this in pounds. You'll have to see, does your table handle body weight? And you're going to find that is one of the dimensions. So yes, it is. It's there. We want to know, do we fit the thin or the heavy? It's like, well, if we design it for the thin, that means the heavy couldn't use it. So let's design it for the heavy. If we stick with our heavy standard that we've gone to trying to accommodate 95th, we'll go with our 95th percentile body weight. Looking off your table, you'll need to decide, do you want the male or do you want a 50-50 mix? And so again, just taking it the easy route, let's go with a 50-50 mix of male-female. You're going to find that is 226.8 pounds. Okay, so 226.8 pounds. On page 51, you'll note they do have an error in their units. That should be pounds. I think they have kilograms. It should be pounds. So page 51 does have pounds. You could add in 1 to 5 pounds for clothing. That would be fine. That would make sense. And so oops, I think I copied this down. This should be 226.8. 226.8. So you could always add in a pound, 1 to 5 pounds for clothing, which bring you to 227.8 to 231.8. Okay, so that would be your best guesstimate. If you go in and look at how much these ladders actually will hold, you go to buy one, you're going to find that it's 225 pounds. And so our guesstimate on this, using anthropometric data that's found in our book, is very close to what they're actually rated for. Unfortunately, they're not really rated to add in 20 pounds of tools and 5 pounds of clothing and so on. It's pretty much right at the 95th percentile 50-50 mix. Okay, so that takes care of some of the numbers. Now if we just go back to some of the constants of anthropometry, the recommended height of common work tasks are based on which anthropometric dimensions? The first thing we're going to look at, the recommended working height of the hands. Okay, and so whenever you are working at a workstation, you want to keep your hands close to your body. You don't want to lift your arms overhead. You don't want to lift them out to the front. You want your arms at your shoulders to be hanging down by your sides. You're working, and so your hands will be in front of you. You typically form a 90-degree angle at your elbows, and so you want your hands to be at elbow height. So you want your hands to be at approximately elbow height. They're typically above elbow height for precision tasks and below elbow height, slightly below for heavy work. Okay, but the first step is elbow height. Recommended starting height to lift a box. Okay, so you're doing a material handling activity, you're lifting a box. If you start with your hands at elbow height, if you don't have the arm strength, so if your employee doesn't have the arm strength, they're typically going to extend their back. They're going to bend their back backwards to try to lift the box. You don't want that to happen. And so instead, whenever you're picking up boxes, you want to be able to use your legs to add some power, your trunk and so on. You want to use more of your muscles, and so typically the starting height is at knuckle height. If you're doing a lift, doing material handling, if you start at knuckle height, you don't have to bend over, but it gives you enough room to use some of your other muscles throughout your body rather than just relying on the muscles in your arms. Okay. So working height is typically elbow height, unless it's a lift and you start at knuckle height. We were looking at maximum control height. If you've got minimal force and infrequent use, we saw earlier that it is your functional overhead reach. Functional overhead reach. And then if you change that to require some force or if add in frequency of use, the vertical height range. We saw that the highest would be shoulder. You don't want people to reach over their shoulder very frequently. And then height range, what's on your lower side. If you put your arms down, what's the lowest you can bend without or reach without bending over? You're going to find it's the knuckle height. Is why I recommended that for our starting height for lifting. But shoulder height down to knuckle height. So shoulder height down to knuckle height. And you're going to find that it's actually a 5th percentile shoulder height and then a 95th percentile knuckle height. Okay, so that's the height range if you're setting controls that are used frequently. Consideration of some allowances. We've said shoes. All the anthropometric data in our tables, it does not consider allowances, has minimal clothing, no shoes, and so if you require shoes in your workplace, you've got to add in the shoes. Some of the problems I've given you also accommodate slouching. Throughout the day, people will slouch. They don't always stay fully upright, and so it's better if you accommodate that into the problem. Your slouching will make you shorter, and so you'll be subtracting off an amount for slouching. Some of your problems also consider product contribution. For example, looking at this workstation, which a person looks like he's working on some sort of technology, it might be a hard drive type of thing, speaker type of thing, who knows what it is. But you can see that because he's working up higher, he's having to work in an awkward posture. And so if he works on all heights of the product, that might be reasonable if he doesn't raise his hand too much. And by the way, this posture is wrist flexion. But if he's constantly at this height, this is his only task. He's got one of those minimal tasks that he does the same thing repetitiously all day. You do not want him to stay in this posture all day. And so you would lower the workstation from elbow height. You would lower it down by this height here, this partial product height. Okay, so workstations, you may need to accommodate them for the product size, product dimensions. And then finally, some notes about your anthropometry tables. Comparing page 48 and 49 to 50 and 51, and oops, I mistakenly early said 50, 51, 52, 53. I'm sorry. But comparing 48 and 49 to 50, 51, you're going to find that 50, 51 is in inches and pounds. So inches and pounds. And 48 and 49 is your metric. I do have a few practice problems where you convert from metric to your SI units, or SI units to back to metric. That's so you're familiar with both, just in case you run across both. Second thing to note is what population are these based on? And typically within the tables within this book, they'll tell you that what the populations are. For example, the populations for the anthropometry, they are, for the most part, military populations. So they've measured soldiers. Taxpayers have paid for that, and so hence that data is free. Okay, so it's cheap for us to use. It's available for us to use. If you go by, some companies are forming conglomerates to take measurements on body sizes. Typically, they've paid for it, and so if you want to use it, you've got to pay for it too. So it's not as easily accessible. Okay, so basically we're working on military type data. So that's what it's based on, typically thousands of people. There is a note, there are some values provided that they will give you what I use non-parentheses, so no parentheses, and then some of them are parentheses, right underneath them have values in parentheses. I want you to use non-parenthesis data. These are based on thousands of people measured. These are based on 50 to 100. Statistically, more is better, and so I want you to use non-parenthesis data if you can. Those are what my answers are based on. And then lastly, the data is good for the United States, North America, South America, Europe, and many African nations. Okay, so we all have relative body sizes in that grouping. If you have a facility in Asia, Asian are typically smaller. This data is not as good, and so you'd have to provide another data source that's fit to those in your Asian nation in particular. Okay, with that, I think I end this second part, or part 2 of the first week's lecture on anthropometry. The next part of the lecture will pick up and look at grip strengths and postures.